Today we're going to talk about sorting in competitive programming, and then the portal code is sorted. If it doesn't work, please let me know. And yeah, that's the link to the slides is here. It's tinyurl.com/ICPC beginner/fall21/-3. So we don't have the projector today. So if you could join the Zoom meeting using this link, that would be nice. Sorry about this mishap. Didn't expect this to happen. Okay. I just want to make an announcement before I start today's presentation. Our ACM internship application is currently open. So if you're interested in working on an ACM committee, not necessarily ICPC, but any committee like ACM AI, ACM hacks, if you're interested in working with people, right, in ACM, feel free to join to submit an application. The application is due this Friday, I believe. And speaking from my experience, it's really fun working with people. It is a lot of work, but it is really fun. And it's definitely a worthwhile experience. If you want to get the most out of your ACM experience, I recommend you to try and apply to join ACM. Okay, so let's get started. Today we're talking about sorting, but exactly what is sorting? Wait, oops. In English, it just means putting things in order, right? But in computer science, it can mean like different things. You can put numbers in order. For example, we have an array here, array of integers. You can put them in order into a specific order. You can also put characters in order. For example, ACB, after you sort it, it will become ABC. Similarly, you can also sort a lot of different things in computer science, like strings, pairs, tuples, so on and so forth. But how do you sort? There are many different sorting algorithms in computer science. Hello. The link to the Zoom meeting is here. We don't have a projector today, so you might have to join the Zoom meeting to see the slide. Also, the link to the slides is also available in the Zoom meeting. Okay, so there are many different sorting algorithms, starting from the easier ones that you might heard of: bubble sort, insertion sort, right? And then there's some faster ones like merge sort, quick sort. And then there's also a very interesting one that, in my opinion, is the best algorithm. It's called BOGO sort. Has anyone of you heard of it before? BOGO sort? Nice. Do you like it? Exactly. Okay. So if you haven't heard of these sorting algorithms, if you haven't heard of these sorting algorithms before, don't worry about it. You'll learn a lot about them in CS31 and CS32. But I think it's necessary for me to tell you about BOGO sort, because the idea of this sorting algorithm is just so brilliant that every computer science major should know about it. Essentially, when you have a number, an array of number, and you want to sort it, the BOGO sort algorithm basically just says you should just randomly shuffle the array, and then eventually it will become sorted. So yeah, that's basically it. Potentially, yes. And then in C++, the default implementation of of the sorting algorithm, like of the sort function, uses intro sort, which is a combination of quick sort, heap sort, and insertion sort. And then on the right-hand side of the slide, you can see visualization of a sorting algorithm in like action. This is shell sort, I believe, and it looks pretty cool. Oh, I have a video to play here. Right, yeah. I can share audio, right? Share down. If you guys want to hear this video, I recommend you pull out your headphone. If you don't have it, well, I'm gonna turn on the the subtitles. No, it's not. Wait. Okay. Hopefully you understood that joke. If this doesn't convince you to learn about sorting, I don't know what does, right? Even the president of the United States needs to know some sorting to become the president. So as a CS major, or like if you're even interested in CS, you should know about sorting. Okay, let's move on. Here is a snippet of code that help you to sort in C++. First of all, you need to include algorithm. At the top of your code, you need to include algorithm, which is a library that has a lot of implementations of different algorithms. And the sorting algorithm is also in there. Or alternatively, you could also just include bit/standard C++.h. This library includes everything, as we mentioned before. So with this, you don't have to worry about the other, including all the other libraries separately. And then inside your main function, first of all, if you want to sort something, you have to have an array or a vector, right? If you don't have something to sort, then there's no point to sort anything. So yeah, we first declare a vector, and then we give it a value, right? This vector is currently has 5 values, 10, 8, 6, 4, 2. And then we just called sort. The function is implemented for you already in the library. So you can just call sort, and then you pass in 2 parameters. The first one, vec.begin, is a pointer to the beginning of the array or vector. And then the second parameter is a pointer to the end of the vector. You don't have to know what the pointer is at this point. So if you need to use this, just remember the syntax: vec.begin parenthesis and vec.end parenthesis. This should do most of the work for you. And then finally, yeah, right. So this sort function will sort the array in place for you. What this means is that after calling this function, the original array, in this case vec, will be in a sorted order. So now if you access the last element of the vector, vec4, this should print out 10 rather than 2. Does anyone have any question? Is everyone good? Okay. Here's more code that you can use to sort arrays and vectors. First of all, if you want to sort an array, you pass in 2 parameters. Again, you need to pass in 2 parameters. The first one is the name of the array, and then the second one is array plus the length of the array. This syntax is very confusing at the moment, probably, but once you've learned once you've taken CS32, you should be able to understand it. For now, we'll just skip the details and put the code here so that you can reference it later. And then if you want to sort an array in descending order, or like you want to sort a vector in descending order, you could pass in a 3rd parameter. And then wait, shoot. For the third parameter, you should pass in greater int parentheses. Again, this is just a funky syntax of C++. If you want to know more about it, you could search it up on Google, but I don't know the nitty-gritty of this syntax yet. And finally, you could also sort an array with your customized function. So for example, if you don't want to sort in ascending or descending order, if you want to sort an array by like how pretty they are, how pretty the strings in this array like are, you could define a function yourself and then pass it into the sort function. Again, the details will be accessible on Google, like you can find it on Google. And then now let's talk about when and why you want to use a sorting algorithm in your code. First of all, when the problem is about sorting, like when the problem explicitly asks you to sort something, I think you should sort. You should probably sort it, right? And then also when the elements of the array have an intrinsic order, you want to think about sorting. Not necessarily like you don't necessarily have to sort, and sometimes you don't need to sort, but the idea of sorting should come to your mind, and then you should think about whether or not you want to sort. And finally, you can only sort when the current order of the array doesn't matter. Because again, as you've noticed, the sorting algorithm in C++ at least sorts the array in place, which means after sorting, you will be no longer you won't be able to access the original order of the numbers or strings in the array anymore. So in this case, when the current order of the array doesn't matter, that's when you can store the array. Otherwise, you might have to store the array elsewhere and then make sure you don't lose the original order. And why do you want to sort? First of all, sorting makes it easy to find the nth element in an order, right? For example, if you have a really messy array, and then you want to find the nth smallest element of this array. For example, if you have like 5, 3, 1, 2, 4, if I ask you to find the third smallest element, it would be really hard, right? But after sorting it, you would know that the third smallest element would definitely be in the third position. And that's one reason why you want to sort an array. Another reason is that some algorithms require you to pre-process the array, like sort the array before you use the algorithm. This brings up a really important technique in CS. It's called pre-computation. The idea is similar to why you would want to sort your desk, clean up your desk every once in a while. It makes some later tasks easier. It doesn't necessarily directly help, but it makes some later tasks a lot easier. Okay, now enough of the conceptual stuff. Let's take a look at an example. This question is called Cetiri. I'll give you guys like 5 minutes to read the question and then try to come up with a solution. It's a very the idea of the problem is very simple, so you should be able to understand it quickly. And yeah. Okay. Okay. Hopefully you've had some time to think about this question. It doesn't seem to be very hard, right? You are given three numbers, and then you want to find like the missing one that together with the other three numbers form an arithmetic sequence. However, when you try to code this problem, it might become really annoying, right? You have to write a bunch of if and else statements to figure out which number is the first number, which number is the second, and which number is the third. Now, the solution to this issue is that you can sort the array. And once you've sorted the array, you immediately know which number is the first one, which number is the second one, and which number is gonna be the third one or the fourth one. For example, let's take a look at this array, 32, 31, 34. Initially, it is very messy. But once you've sorted it, you'll see that the first number is 31, the second number is 32, And then the third number is 34. One number is like, and then you can just go through the array, look at the difference between the two elements in the array. In this case, the difference between 31 and 32 is 1. The difference between 32 and 34 is 2, which means a number must be missing between 32 and 34. And then you know that the number that's missing is 33. In the case that there's no number missing in like inside, in between the largest number and the smallest number, you can just add like a random number either at the very beginning or at the end. So that's the solution to this problem using sorting. As you can see, once you incorporate sorting into the solution of this problem, writing the code, at least it takes a lot less time to write the code. Okay.
All right, so we're going to do a quick interjection here and talk about big O notation and what it means. So mathematically, we go to the definition. We have O of f of n represents the asymptotic upper bound of a function of n. So for example, it can be something like n squared or log n, where n is just some number. And then, so how do we apply this to programming? So if we look at it, what it's basically trying to say is how many times do you have to go through the input data or do certain operations using whatever algorithm you're using to solve the problem. So n in most cases represents the number of numbers that you receive for a problem. So if you're given like an array of n numbers, that's the n that we're talking about. And n is going to depend on the problem that we have. So let's say, for example, we have some functions. So if we have, we're just going to declare a number and we're going to sum up all the values in an array, right? So if we look at the first operation, that's the first line is going to be one operation. And then we're going to go to a for loop that loops n times. And inside of that for loop, we're going to have one operation. So if we add this all up to count how many operations we do, so operations are things like setting values to certain variables or adding, multiplying, stuff like that. So if we add it all up, we get 1 plus n times 1, so we get n plus 1 operations. And then we can see that when n becomes really, really large, so let's say n is 1,000, right? The total sum of operations we do is going to be 1,001. And because that's so negligible when we get to large n, we only care about this first number, so this n, right? So we write this as O of n, or we also like to say it's a linear time function. Okay. So for this one, right, we're going to nest this for loop inside of another for loop that goes for 4 times, right? So can anyone tell me how many operations are in this code snippet? Any thoughts? Yeah. Yeah. So we do the one line as usual, right? And then we go through the inside loop 4 times. So we do 4 times however many is in the inside for loop. And then that happens n times. So we get 4n plus 1. And then, so the complexity here, we're going to take that higher term, which is 4n. And then we don't care, we can drop the coefficients in front of the higher order term, because that's like, we don't really need to worry about that when we're looking at long term or like large n. So this is also a linear time code snippet, even though there's 2 for loops. Okay. And then finally, we have our last snippet here. Can someone else tell me how many operations we do for this? Okay, so it's similar to what we did last time, right? So we're going to have one operation beginning, so we're going to add 1, and then there's going to be 2 for loops. But this for loop, we changed it going from 4 times to n minus 1 times. So we're going to multiply it by n minus 1 times n instead. So if we multiply this out, we get n squared minus n plus 1 operations. And so in this case, the highest order term is n squared rather than n. So we drop everything else. And we can think about it like, oh, if we put in 1,000, right? If n is 1,000, then we get 1,000,000 minus 1,000 plus 1. And those smaller terms don't really matter, right? They don't matter by like a factor of 1,000. So we drop that. So our complexity for this one is going to be n squared. So things like insertion sort or bubble sort, if you guys know what that is, it's like this is something similar where you have nested for loops. And so why are we learning about this? Why are we learning about this big O notation, this complexity, which is another way we call it? It's because we can look at the input size of certain problems. So if they give you 10 numbers, you can say, oh, I can do a lot more operations than if they give you maybe 100,000 numbers, right? So for example, there's a bunch of different complexities here, O of n, big O notations on the right here. So you can have stuff going from factorial all the way down to constant time. So that O of 1 on the very bottom, that means constant time. So anything, if it takes 4 operations, if it always takes 4 operations or always takes 5 operations, that counts as constant time. So we can see based on the input size, so that's going to be our n value, whether or not our algorithm is going to work in the time constraint. So normally when you submit a problem, your program can only run for a certain amount of time. And generally it's like 1 second for C++ and more for slower languages. But generally you're able to do around 10 to the 8 operations. That's about it. So you can kind of think about it like that. So you can see if you have an n log n algorithm, right? If you multiply it out, you'll get roughly 10 to the 8 operations if you have an input size of 10 to the 5 numbers. So if we look at actual input specs from problems, you can see that, so for example, this first problem gives us 2 integers n and m. So we just look at n, so let's say our function only cares about n. And so we know that we're trying to look for an algorithm that has a complexity of n log n, right? Or anything faster, right? Anything faster will also work. Or something like constant time or linear will also work. And then for the second one, if we have some smaller size, so this only goes up to 200, we know we can maybe have a little bit less efficient algorithm that's n squared or n cubed. And yeah. Does anyone have any questions? So yeah, so basically big O is just kind of like a heuristic that we can use when looking at problems. So if you see something that has a really small n, you'd be like, oh, maybe I can think about it like a dynamic programming problem or something. And if you have something that's really big and your algorithm is getting really complicated, you can kind of be like, this is probably the wrong direction, step back, and then try and approach in a different way.
Okay, let's take a look at a second example. It's called Basic Programming 2. The link to the problem, the problem is also inside that example contest. And you should be able to access it, right? This problem is very different from a normal competitive programming problem. As in a normal competitive programming problem, you wouldn't see so many different subparts, subsections. But in this case, I included this problem because I think it's a really good practice for you to like practice using sorting in your code. Yeah, I'll give you guys, again, 5 minutes to take a look at the problems and then try to solve them. I don't think 5 minutes is enough to completely solve this problem, but maybe just look at the first 3, which I'll be going over very briefly. Yes. Okay. I think that's 8 minutes already. Hopefully you've had some time to think about the problems. And Yeah, let's take a look at the first example. The first task of this problem asks you to find two numbers from an array that sum up to 7,777. The straightforward solution would be to check each pair of numbers to see whether or not they sum up to 7,777. But there's an issue with this solution. Recall what we talked about when we were talking about the big O notation, right? N choose two, like in this case, if you want to check each pair, your code will go through at least N choose two pairs of numbers. And that is equal like almost N squared pairs in total. And then in this problem, it says N is smaller than or equal to 200,000, which means N squared would be somewhere around 40 billion checks, which is too large for modern computers. So is there an easier way to do the problems? Yes. And that would be, you could sort the array first. After sorting the array, you could apply a technique called the two-pointer method, which is going to be really useful if you do some leak code and you want to do coding interviews in the future, right? This is a very, very famous technique that's always tested in coding interviews. And it's also really useful in competitive programming. So the idea is that you want to sort the array first so that you don't have to check some unnecessary pairs. Let's take a look at this example. If you want to find 13, two numbers that sum up to 13, and you have an array of 1, 2, 4, 6, 7, and 8. Now, initially, you would have two pointers pointing to the beginning of the array and the end of the array, a left pointer and the right pointer. I'm just calling it that, but when you're implementing this problem, you could just have two indexes, and one like indicating which one is the left, and then one indicating which one is the right. Now, as you notice that 1 plus 8 equals 9. It's smaller than 13. So we want to increment the left pointer and then move it one slot to the right. Now 2 plus 8 is still smaller than 13. We want to move the left pointer one slot to the right again. 4 plus 8 is still smaller than 13. We do the same thing again. Now 6 plus 8 equals 14, which is greater than 13. And because so now we want to decrease the size of the larger number and then move the right pointer one slot to the left. As you can see, we get 13, and that is our final target. If you spend some time to think about it, you would notice that after sorting the array, this algorithm only takes O of n time, which means it only goes through the entire array once, which is a significant improvement from the O(n squared) solution we had initially. And if you wonder why this solution worked, like why can you just move the two pointers? Why do you not have to check the other pairs? The reason is pretty difficult to talk about. You can spend some time later on, like after the meeting, and then we can discuss and see if you know exactly what is going on. So for this task, the terminal condition, or like you would write a while loop, right? And then once you found the target sum, you want to terminate the while loop. Otherwise, if the sum is greater than the target, you want to increment the left pointer. If the sum is smaller than the target, you want to decrement the right pointer. Now, if no pairs sum up to the target, then the left pointer and the right pointer would eventually meet in the middle and point to the same number. And this is also when you want to terminate the loop. And this basically tells you that it's impossible to find two numbers that sum up to the number we want. Now, the second task of this problem asks you to determine if there are any duplicates in the array. Approach one would be to put every number in a hash set if you know what that is, and then compare the size of the hash set to the size of the array. But this approach requires you to know what hash set is. If you don't know about it right now, don't worry. This is, I think, the content of CS32. So you'll learn about it very, very soon. But there's another approach that also works. And it is to sort the array and then traverse through the array and then compare the neighbors inside the array. Notice that on the right-hand side, I have an example of a sorted array. All the duplicates are placed adjacently, right? If two numbers are the same, they must be beside each other in the array. So using this trick, you can easily find whether or not there are duplicates in the array by just checking the two adjacent numbers in the array. And here's the code that implements the solution. You can always come back to it to take a look at it later. And then the third task is asking you to find the integer that appears greater than n over 2 times. So essentially, the number that dominates this array, or the majority element of this array. Notice that if the array is sorted, the duplicate, again, we want to use the same discovery we made for the last task. Duplicate numbers always appear side by side. So once we've sorted the array, we can just traverse through the array and then count the number of appearances each number have, right? For example, in this case, you start from the leftmost point, it's a 2, and then you go over to the second slot, it's another 2. So you know there are 2 2s. Now, the next number is 3, which means you can stop keeping track of how many 2s there are. You can start counting how many 3s there are. As you notice, there's only 1 3. So moving on, we see a 5. And then keep going on, we see 3 more 5s, right? We can just, if we keep track of how many 5s there are, we can find out that actually we have 4 5s. And then that is more than half of the array, half of the array size, which means this is the target we want to find. Okay. This is the piece of code that implements the solution. Again, feel free to take a look at it after the workshop. Now, I don't know how many of you have looked at the fourth task, and it is pretty simple once you sorted the array. And the same could be said about the fifth task. If you're interested, definitely take a look and then take some time to try to solve it. It's a really good practice. So this concludes our workshop for today. We'll have a mini contest coming up. But before that, I would like to ask you guys to provide us with some feedbacks. We really appreciate you coming to our workshops, and then we hope to make our workshops better in the future. So if you could click on this link and then maybe take 2 minutes to give us some feedbacks, that would be really nice. Okay, so if you've already filled out the form, the feedback form, feel free to start working on the contest for today. And I want to mention that at the end of the quarter, we'll pick the top 3 cumulative performer on these after workshop contests and then give them a prize. So hopefully that would be some really good motive for you to work on our contest problems. They are very interesting problems, and I think after coming to our workshop, you should be able to solve them. If you don't, feel free to ask any of the officers. We would be happy to help you with them.